going to start learning about logistic growth now. And I'll just tell you right now, I won't beat around the bush. Exponential growth, you grow up and up and up and you just get bigger and bigger and bigger. Logistic growth, you grow exponentially and then something happens. Maybe it's the environment, maybe it's whatever. For whatever reason, your growth is capped. For whatever reason, you start plateauing and then you start approaching a maximum population value. And when that happens, when your growth starts off exponential, but then starts leveling off, we call this logistic growth. And this is a type of growth that happens with populations in biology. It can happen with many different situations. It can happen, we're going to talk about a flu epidemic, and this is the type of growth that happens with a flu epidemic. If we talk about the spreading of a rumor, For example, how many people here have heard that yesterday, in the course of honoring Native Americans, President Trump actually did a racial slur against Indians while he was honoring them? Okay, how many people know about that? Okay, well, pretty soon it'll be all of you. But right now, since it just happened yesterday, it's just a few of you. And the number of people who hear that rumor, which it is a rumor. I mean, it happened, but it's also a rumor because it's spread by word of mouth or by whatever. But pretty soon all of you will hear about it, and it'll be interesting, So anyway, that's logistic growth. So let's get started. Let's talk about the population of the United States of America, okay? The population, are we starting now? Did we start? Okay, good, thank you. Yeah, the population of the US. Remember, based on the population in the year 1790, and based on the fact that our relative growth rate was pretty much constant for the next 60 years, really for the next 70 years, we got this equation. We've got the population for T, P of T, equals 3.9 times e to the 0.0296 t, where t is in years, not decades. We decided to go with years, or I decided to go with years, and P of t is in millions of people. And we found yesterday that equation worked for the first 70 years of our nation's history, okay? But we found that it didn't work for the 80th year. It didn't work for 1870. That is, from 1790 to 1860, the formula works well. And then in 1870, the predicted population, using that formula, ended up being, what was it, like 42 million or something like that? I forget, 41.6 million, I think it was? 41.6, say again?
Yeah, that's right.
41.6 million? Okay, but the actual population ended up being way lower than that. I looked it up actually, and I had a bad number. I said it was 38.6, but it actually ended up being 39.8 million. So it was actually almost 2 million short, not the 3 million short that I thought it was yesterday. And then you guys answered it right when the bell rang. What can explain why our population didn't increase as much as we would have thought? Yeah, Civil War. Right, we lost 600,000 people just due to battle deaths, and then who knows how many babies didn't get born because they didn't have daddies available to, impregnate their wives because they're all dead, So yeah, so we got 2 million people less in the United States in 1870 than we would have predicted. And then now here's the next question I want to ask you. How about the year 2000? Oh, and remember, T is years. Actually, T is the number of years after our first census, after 1790. So what about the year 2000? Let's go ahead and use this formula to predict how many population there would be in the United States in the year 2000. That means T would have to be 210, And so P of 210, which is going to get me to the year 2000, is going to be 3.9 times e to the 0.0296 times 210. And let's see what's predicted by this formula. Do I have it written here, or do I have to actually punch it in my calculator? Does someone feel like punching it in their calculator? What do we get when I stick 210 into this? 1,952.7. So 1,900, you say?
Yeah.
Okay.
52.
Okay, I'll just go with 1.95 billion. Okay, so that's what we're predicting, 1,950 million. 1,950 million people, which means 1.95 billion people. Is that true? Do we have approximately 2 billion people here in the United States?
No.
Yeah, not even close, right? Not even close. So we know, and I'll tell you right now, populations can't grow exponentially forever, okay? We're not gonna just grow larger and larger without bound. At some point, what's going to stop the growth? And you tell me, I mean, those of you who know history, why did we stop growing exponentially? What happened? What's happening with the United States that made us stop growing exponentially?
Lack of space.
Yeah, lack of space. What was happening in the United States from 1790 to 1860? Or and beyond? What's that?
Expansion.
Yeah, we were expanding, right? What did we get? Tell me, what were the big ways that the United States expanded? Like in 1802, I guess it was, or 1803, what did we get?
Louisiana Purchase.
Yeah, Louisiana Purchase. 1845 and 1848, what did we get?
Mexicans.
Say again? Yeah, the Mexicans, all the Mexican lands, right? We did the Mexican-American War, as we called it, and got a bunch of land from Mexico, right? And so on. And we hammered things out with Britain so we could get the border between, Washington and, the Canada. But there came a point when we stopped getting new territory, and then that's going to limit our growth. We're not going to be able to grow exponentially anymore. Okay, great. And so that type of growth I talked about at the first part of the class, logistic growth is what happened, and it took over. Let me just show you. We in the United States, we haven't started leveling out yet that much. It's going to be interesting to see. Let me just see this. And anyone who's watching on video, I apologize, because I don't know, I'm just kind of going slow on this, and it's not that interesting, but that's okay. People watching on video, sorry. There you go, let's see here, oops, stupid thing. I'm using technology here. I'm using my graphing calculator on the overhead projector. Okay. So, is that focused? No. What the heck? Is this bad? Huh. Why is it not focused? Oh, wait. My overhead projector is...
Not spoken.
Yeah. What am I going to have to do? Just press it down? There you go. Sorry, kids. Yeah, I just did brute force. Oh, now the red button's working. See, let that be a lesson to you. If any technology doesn't work, just use brute force to fix it. Okay, great. So here's what's happening. Looking at my stats, okay, I've got an L1. I've got the, oh wait, not L1. L4, I've just got the first 70 years of our nation's history. This is, I have the numbers 0 through 70, which would be the same as 1790 through 1860. And then in L2, I have just the populations from 1790 to 1860. And so I'm going to plot just those guys. So that means that X list has to be L4, for those of you who are fans of the TI-83, and the Y list has to be L2, and then I do zoom, wait just a second, 9. Okay, and then I need to, okay, what I did here, and I'll just clear this. Okay, so do you see here, I'm getting what looks like exponential growth. I mean, you look at that graph, you know, you look at those points and you go, hey, that's looking like e to the x. That's looking like exponential growth. And in fact, I can get the logistic equation. I can go stat calc, and then not logistic, but the exponential. I'm going to use exponential regression. And of course, I have to use L4 as my x and L2 as my y. And then I get this equation, okay? And I just want to show you guys. This equation I get with exponential regression is approximately 3.9 times 1.03005 raised to the x power. That's the way my calculator does it. Here in calculus class, we like to have my base be e, so I'm actually going to call this e raised to the log natural of 1.03005x. And then, this is stuff you don't have to know how to do. I just want to show you. And then the log natural of 1.03005 ends up being the k that we found yesterday, 0.0296. And I guess I should call it t instead of x, because it's number of years. Okay, so the point I'm making is this is the exponential graph that we found yesterday, the exponential equation we found yesterday. And if I can put it in there, statistics, equation, regression equation, there's the equation, then I graph it. And the equation goes through my points perfectly. That's exponential growth, and it goes through all the points from 1790 to 1860. But now, what if I look through the year 2000? So now L1 is going to be all my years through the year 2000, which means through 2010, because 1790 is 0. So 210 is going to be the year 2000. And then L3 is all of my populations through the year 2000. And the year 2000, the population of the United States was 249 million. So let's go ahead and do that. Just one second. So now I'm using L1 and L3, zoom 9. So there's the growth of the United States of America. And then my exponential growth goes crazy. I just want you to see that we were growing exponentially for the first 70 years of our existence, and then we stopped growing exponentially. And we started growing, and if you look in the last 5 or 6 decades, last 5 decades, it's almost linear. I mean, we're not looking exponential anymore. Something else is happening. And so what's happening with our logistic growth curve, which we're going to learn about more in earnest tomorrow, okay, we're probably about right here. We're about right there in our logistic growth curve. So if people say, oh no, the United States of America, we have too much population. Well, not really. We're going to learn later that based on the growth rate of the United States of America right now, you know, our maximum population could probably be, you know, 600 million. We could fit 600 million in this country and still be fine. Yeah.
But that's just the amount of people that are having kids, right?
No, these numbers are everyone, men, women, and children.
No, I'm saying like the growth rate is just people having kids, right? Or is that people like also coming into the country?
Oh yeah, no, it's all of it coming in. You take the number of people having kids and the number of immigrants, you subtract the number of people emigrating and the number of people dying, and that's going to be your absolute growth rate. Yeah, so it's got to include everything. Yeah, and what's happening in all of the Western countries is, you know, we Americans aren't having enough kids. And it's more true for other countries than it is for us. And so we're getting this phenomenon where you're getting this population aging and we're not being replaced with enough young kids, you know. I mean, the only way we can keep our economy going is to essentially import young workers, and then they can work and pay taxes to help care for the old people, you know. That's why Donald Trump is trying to keep all the people from other countries out, so that we don't do that or something. I'm not sure what he's trying to do, but we need those young workers, you know. Okay, so that's America. Let me think if there's anything else I wanted to say. One thing I want to talk about, right here, this is the 1920s and the 1930s, where suddenly our growth rate really dropped. What happened in the 1920s and really 1930s mostly? Right there is the decade. This is 1940. Okay, this is 1930. So we grew really good from 1920 to 1930. Then we had almost no growth from 1930 to 1940. Then we resumed growing again by 1950. What happened here? What happened between 1930 and 1940 to make us not grow?
Great Depression.
Yeah, the Great Depression. So I want you to see, you know, historical stuff affects our math, you know. You read right here, Civil War, you know, right here, Great Depression. Right here, what special thing happened to suddenly resume a gigantic growth rate? What's happening here, here, and here?
Baby boom.
Yeah, the baby boom. Yeah, we're suddenly having this incredible growth of population due to the baby boom, and now we're pretty much linear. We're not doing the baby boom anymore, you know. Alrighty, so anyway, I don't know if you're getting anything out of this, but it's fun to talk about. Let me see what I wanted to do. Yeah, let's talk about, I'll come back to the United States like tomorrow.
So Shannon, why do you have part of the homework circled in green?
Because if I don't get to it, then I'm going to cross it out.
Um,
So your homework may end up just being these problems and not the stuff in green, because the stuff in green is logistic growth. So that's it. I was just, you know, and I knew there was a chance we wouldn't get to it, and that's okay. Okay. Alrighty, let's go ahead and actually talk about logistic growth. Here comes the math portion of our lesson. Logistic growth. Okay, let's say there's a flu epidemic at Etiwanda High School. Flu epidemic at Etiwanda High School. Let's let P equal the number of kids with the flu. Okay, P is the number of kids with the flu. T equals the number of days. And so let's talk about what the absolute rate of change of P with respect to T is. That is, what's going to determine how many kids in a given day, let's say, get the flu? The number of kids per day who get the flu. What's going to determine that? Like what sort of thing would make it so that a lot of kids could get the flu on any given day?
Coughing.
Okay, coughing. Ease of transmission, right? If it's very, very hard to get the flu from other kids, then no one's going to get the flu. And your DPDT is going to be low. But if it's incredibly easy to give someone the flu, if just breathing on them gives them the flu, then your DPDT is going to be pretty high. Because all kids have to do is breathe on each other to give each other the flu. You see? And so, yeah, DPDT, I'll just say depends on 1, ease of transmission. What else is it going to depend on? Like, consider under what circumstances could you have it where only 2 kids in this whole school, only 2 kids got the flu today? And under what circumstances could 100 kids get the flu? What would you need?
They'd have to be in the finance.
Well, I didn't hear what you said, Andrew, but I'm also going to ignore you because I want someone else to answer. What else could cause, what would have to be true? What would have to be, under what circumstances could a very few kids get the flu or a lot of kids? Yeah, Omar.
For a lot of kids could already have it.
Thank you. You need a lot of kids with the flu in order to transmit it to lots of kids, right? You guys okay with that? So you need lots of kids with the flu. But tell me, it depends on one other thing. Could you imagine a scenario where you've got lots of kids with the flu, but on a given day, only 1 or 2 more kids get the flu? And Omar, I love you dearly too, but let me see if a third person can answer this, because I know you know. Tell me, what else does it depend on? Is there a scenario where a lot of kids have the flu, but only 1 or 2 kids get the flu that day? Yeah, Kylie?
If everyone already has the flu.
Thank you. If everyone already has the flu. Beautiful. I'm sorry to cut you off. What were you going to say? Yeah, if everyone already has the flu, right? That is, not only do you need a lot of kids with the flu, you need a lot of kids without the flu, right? Lots of kids without the flu. Okay, if you've got that situation, then you can have a lot of kids getting the flu. So dp/dt depends on all of those guys. So I can make a differential equation. I'm going to say let m equal the carrying capacity. When we talk about the carrying capacity, that's the maximum that the maximum population that an environment can support. The maximum population that an environment can support, that's your carrying capacity. Well, here at Etiwanda High School, what's our carrying capacity going to be?
About 4,000.
Yeah, about 4,000. I think it's like 3,850 or something like that. Yeah, the number of kids, the total number of kids at EHS. About 3,850, approximately. Okay? And so now I can get a differential equation for dp/dt. dp/dt is going to be proportional to the number of kids with the flu. Proportional to the number of kids with the flu. But it's also proportional to the number of kids who don't have the flu. And what would I call this quantity? Yeah, m minus b. So it's proportional to the number of kids without the flu. And then I need a constant of proportionality. And that constant of proportionality is going to express ease of transmission. I'll call that constant k for now. The bigger k is, the easier it is to get the flu. The smaller k is, the harder it is to get the flu. Well, you're going to learn later that this differential equation is going to get us our logistic growth. It's going to get us exponential growth initially, and then it levels out to be just a plateau. Okay? And this comes from this idea. And any situation look at, when you look at predator-prey, when you look at the spreading of a rumor, when you look at anything that follows logistic growth, you're always going to be able to say, okay, the absolute rate of change depends on 3 things. The number of people who hear the rumor and the number of people who haven't heard the rumor yet, and how easy it is to hear a rumor. It's much easier to hear a rumor nowadays than 150 years ago. Things would happen and, someone 200 miles away would never even hear about it for months. Now you hear about stuff immediately, okay? Well, mathematically, I've got to do one thing to change this differential equation. I'm going to factor out m. You're just gonna have to trust me on this. KMP, so I get 1 minus P over M. This makes things mathematically easier. And then this stuff, Km, since I don't know what K is anyway, and all M is a multiplier because M is a constant, I'm going to combine these two together to get me Kp times 1 minus P over M. And that is the differential equation for logistic growth. And that's the one you guys will use over and over and over again. Logistic growth. dp dt equals k times p times 1 minus p over m. Great. Let me see what comes next. Okay. When you solve this differential equation, and you have to solve it by using a process called integration with partial fraction decomposition, something we're going to learn in chapter 8. So I need to just teach you what the formula, what the solution is, without showing you where the solution comes from, because we learned that in chapter 8. The solution ends up being this. M over 1 plus A times E to the negative KT power, where A equals M minus P naught over P naught. There we go. So the next thing I've got to do now is do a million examples with you. We'll do a couple of them today, we'll do the rest of them tomorrow, and then you'll be ready to do logistic growth. Let's do one example together. Yeah, just sure. Here comes example number 1. This is the first example we'll do. I'm going to want you to find dp dt, find p of t, make a slope field, and it's going to be a slope field from p equals 0 to p equals 1.25 times the carrying capacity. And then D, plot the solution. I'm going to show you one example, then we'll do all the rest tomorrow. Okay. What if I told you I had a situation where there's the spread of a flu at some place of work, let's say, and it turns out that the carrying capacity, that is the number of people at that place of work, happen to be 100. So there's 100 people at that place of work. And the ease of transmission translates into a K of 0.04. And it turns out that on the first day of that flu epidemic, there's 10 people who have it, which means that's my P naught. My initial value is 10. To do parts A and B, all I'm doing is mindlessly plugging into the formula. It, all of the conceptual knowledge happened here. Now, it's just, I'm gonna mindlessly use the formula. So to do part A, I want an expression for dp dt. Hey, there it is, Kp times 1 minus P over M. So I'll have 0.04 p times 1 minus p over 100. Are you guys okay that that's my differential equation right there? Where did it come from? Well, it came from this discussion. But now that we've had this discussion, you're just going to mindlessly use the formula. B, let's go ahead and get an expression for the solution. P of t. Well, there's my equation for P of t. Again, no thought required. Just plug in. I've got m, which is 100. 1 plus a. Well, my a is equal to m minus p naught over p naught. So do you see that my a is equal to 9 in this case? 100 minus 10 over 10. So I got 9. E raised to the power of negative kt. And there it is. There's my equation. Let's go ahead and make a slope field. I'm going to have population here and time here. But here's the weird thing. Do you see that my little slopes don't depend on time? My slopes only depend on p. So here's what I'm going to do. I'm going to say, okay, I'm going to go, here's my carrying capacity, m. Here's 1/2, which is 50.
It's 100.
I mean 100, I was thinking of that guy, thank you. M, which is 100, so this is 50. This I'll go with 25. This will be 75. And I wanted you to go up to 1.25 times m. So this will go up to 125. Now, I'm going to get my slopes. And you can put your dots wherever you like, because you're just going to get the same slope for every p-value. Okay. When p is equal to 100, what's my slope going to be? Yeah, 0. When p is 100, this term gets to be 0. So my slope is 0 at p equals 100. How about when p is 50? What's my slope going to be? Well, dp dt at p equal 50 is going to be 0.04 times 50 times 1 minus 50 over 100. Are you okay with that? And 0.04 times 50 is what? 0.42?
Yeah.
So I got 2 times a half. 2 times a half. So you see I get a slope of 1. So at 50, my slope is going to be 1. Unfortunately, the bell's going to ring pretty soon, so we'll complete this tomorrow. So we'll just, but you can guess the rest, I hope. You're just going to plug in 25, 75, and 125 for p and get what those slopes are. We'll complete it tomorrow. So definitely.